Hello everyone, we're going to take a look at outcome 3, part 1, which is dealing with KW, KA, and KB. So part 1 deals with the equilibrium of water, pH, and POH. So purified water has a very slight conductivity that is only observable if measurements are made with very sensitive instruments. We know that regular water out of the tap has minerals such as fluorine, sodium, etc. When we have like a sample of distilled water, we know that we have pure H2O. So we'll just put H2O plus these other minerals, but we have distilled water, we have just H2O. So according to Arrhenius' theory, conductivity is due to the presence of ions. Therefore, the conductivity observed in pure water must be the result of ions produced by the ionization of some water molecules into hydronium ions and hydroxide ions. So we have two water molecules that collide, and we're going to get under 10% of this going on, in which one H is taken to produce hydronium, and then the other H is lost and produces that hydroxide ion. And when we have this reaction here, our Kc is H3O plus OH minus, but over H2O times H2O. But H2O is a liquid. It's a pure substance. It means that we're crossing that off. So our Kc is simply H3O plus times OH minus. And the water ionization equilibrium relationship is so important in chemistry that this particular Kc constant is given its own special symbol and name. This new constant is called the ion product or ionization constant for water, which is Kw. So Kw is H3O plus times OH minus, which gives us a value of 1.00 times 10 to the negative 14 at SATP conditions. The equilibrium equation for the ionization of water shows that hydronium ions and hydroxide ions form in a 1-to-1 ratio. Therefore, the concentration of hydronium ions and hydroxide ions in pure water must be equal. This equality is also true for any neutral aqueous solution. So H3O ion concentration is equal to OH minus ion concentration, which we know that if two things are multiplied by together, we can take the square root to find out what one of them is. So one of these is 1.0 times 10 to the negative 7 moles per liter. The relationship between Kw, H3O plus, and OH minus. The most important point about Kw is that it applies to pure water and also to any solution that is mostly water. This means that this ionization equilibrium will be involved in any other reaction going on in aqueous solution. If that reaction involves hydronium ions or hydroxide ions in any way, we can easily use Kw to calculate either the hydronium ion amount concentration or the hydroxide ion amount concentration in an aqueous solution, if the other concentration is known. For any aqueous solution, since H3O plus, which is aqueous, times OH minus, which is also aqueous, equals Kw, then H3O plus is equal to Kw over OH minus, and OH minus equals Kw over H3O plus. All we've done is rearrange. If we divide on one of these on both sides, we have to do it to the other. So if we want to find our concentration of OH minus, divide this side by H3O plus, divide this side by H3O plus, we're left with OH minus equals Kw over H3O plus. We're going to do a couple examples here. Oops, just zoom my screen in a bunch. How did I do that? Try to fix that. There we go. All right. First example here is a 0.15 molar per liter solution of hydrochloric acid at 25 degrees Celsius is found to have a hydronium ion concentration of 0.15 moles per liter. So H3O plus, we know that. Calculate the amount concentration of the hydroxide ions. So I know my H3O plus concentration. Having application difficulties here. Maybe I'll be okay. We'll keep going here. If I do have issues, I'll break this video in half. Yeah, I'm going to end this video here. I'm going to close out the application, and then I will do the examples here.